All right, so it is Friday, and we have a little bit more of that quantum number crazy stuff that I started yesterday to talk about. I won't get as far as I want to, I don't think, this semester, but what else is new, right? So I hope you have a wonderful weekend. I have pictures of two of my favorite holiday movies. If you haven't seen It's a Wonderful Life, it is a classic. I put a link to the trailer in the calendar on the stream. And then, of course, the original Grinch. I don't care for the one with real people. I like the cartoon one because that's the best one. So, and if you get a chance to watch some movies, you might want to check out these oldies but goodies. All right, so that is enough of that. Yesterday, you got a new note sheet. I uploaded the video, the lecture video from 6th period because I think it went a little bit better. A couple things I wanted to say about this before we get going too far. A lot of you, I'm not going to find my, I was going over this for Wednesday's attendance. I told you you didn't have to do the second one. That's fine. That everybody did fine on this. This slide, most people probably, it's 60% of you anyway, missed this slide. Not a big deal. You obviously played around with the interactive because you answered the other questions. But just be sure you know that wavelength and frequency are inversely proportional to each other. And again, most of you got this. Amplitude, just a little refresh. Remember, that's the height and depth of the wave. So make sure you know what amplitude is as well. A couple of you missed this one. I didn't write anything on this slide, so you might have lost a point for that. I think everybody got this, almost everybody got this correct. Longest wavelength of the electromagnetic spectrum would be radio waves. The wavelengths that have the highest energy would be gamma rays, and they are also the same ones that have the highest frequency. This slide, a lot of people didn't quite get right. So white light is actually all colors of light combined. It's all the wavelengths of the visible spectrum combined together. So that's what white light is. Why do we see the color black? This one's a little harder to answer if you think about it in terms of paint. Yes, the paint pigments absorb all the colors and don't reflect anything back. But when you talk about blackness, it's the absence of light. So maybe that question isn't worded quite exactly correct in the best way to get the right answer. Most of you did this one, and everybody did fine on this. Okay, so any questions on that slide deck? I haven't finished uploading the grades for them. I just scanned them, so I'm going to finish that today. Great. So the other item that you want to have out just to look at is the note sheet from yesterday about quantum numbers. So I'm going to pick up where we left off on that slide show, and hopefully, good. So again, just a quick, oh heck. What are the quantum numbers? Again, they correspond to an electron's address. There's 4 of them. The most important ones are the first 2, and we're going to focus on those. The others are, we'll just hit on them just really quick. They don't pertain that much to chemistry and action, okay? So again, principal quantum number gives you the size of the cloud, which tells you the distance the electron can be. Sublevel is a shape, and we're going to get into that today. Magnetic is the orientation on the axes in three-dimensional space, and then this weird spin thing, which really doesn't apply to anything we have to worry about in chemistry. Principal quantum number is the energy level, how far the electron gets to live. It also corresponds, this is the coolest thing, it corresponds to the periods on the periodic table. And I hope at some point in the class it'll go off for you, and hopefully on Monday we'll be able to seal the deal on that. Again, atoms are like onions, orbits are like onions, atoms are like onions, okay? So hopefully they all have layers, right? And so the layers on an atom correspond to the energy levels that Bohr worked out, that distance, those little steps that you get to be from the nucleus. So sublevels, that's the next one. This is the second quantum number. Sublevels, again, it's abbreviated with a lowercase l for level. They give us the cloud shapes. The first one's really easy. The s orbitals are really easy. They're spheres. Okay, that's cool. After that, it gets kind of crazy. Okay, so s orbitals, this is something you need to know, are spherical. So on my slide, it looks like a circle. Remember, matter's three-dimensional, so there's a sphere. Okay, somewhere at the center of that sphere would be the nucleus. Okay, the next ones are a little bit weird, to say the least. P orbitals. So remember, the sublevels are S, P, D, and F. The P orbitals consist of clouds that are double-lobed blobs. Okay? One of them is around the x-axis, one of them is around the y-axis, and one of them is around the z-axis. That's the magnetic stuff, X, Y, Z. Okay? This blue region can hold a maximum of 2 electrons. All of these can hold a maximum of 2 electrons. 2 in the S, 2 in the PX, 2 in the PY, 2 in the PZ. They don't just stay in those 2 blobs. They could both be on one side. And again, remember, orbitals are just 90% probability of finding the electron there, so they might not even be there at all. The most likely place for them to be is in the close to the nucleus, because electrons are negative and the nucleus is positive. They're attracted to each other. Okay, so these are all overlapping, and they all kind of go together. And I hope the 2 little animations that I showed at the end will help you visualize that. All right, so those aren't too bad. The classic name for these are dumbbells, like 2 blobs with the center handle in the middle. We'll go from there. So again, 2 here, 2 here, 2 here, 2 here. So 3 times 2 is 6, plus 2 is 8. That's a super important number that you're going to want to hang on to. It's called an octet, and we'll come back to that a lot. Okay, so again, the S and P orbital electrons of the highest energy level are the valence electrons for that atom. All right, you ready for this? You've got a picture of it on the note sheet, but the d orbitals are crazy. So since the p orbitals are on the x, y, and z axes, the d orbitals have to fit in between them. Okay, and so they exist. Some of them exist, these clouds, and this time they have 4 lobes instead of 2. Okay, between the x and the y, between the x and the z, between the y and the z. Oh, goodness, there's that. X squared minus y squared. Oh, no, math. And then the next one is just awful. What? That is a shape that somebody smart can figure out how to do mathematically. I can't. Okay, so 5d orbitals. Each one of those can hold, they're not necessarily filled, but they can hold 2 electrons. So again, there's 4 rooms here, if you will, 4 clouds, 4 parts to the cloud, but somewhere in that space, there's 2 electrons, okay? And this one, I just don't even know what the heck to say about that, right? And just when you thought it was getting too weird to handle, here's the f orbitals. Oh, it's nuts. It's nuts. The crazy thing is they have proven these shapes by analyzing atoms and verifying it mathematically. It's possible to do. Look at this, heck. X times 3y squared minus x squared. What is that? Who cares? We don't have to worry about it. It's okay. All right, so again, 2 times 7 is 14. 2 times 5 is 10. 2 times 3 is 6. 2 times 1 is 2. There's something going on here if you remember about the periodic table. But what the heck are they talking about with these shapes? It has to do with mathematical calculations for standing waves. So remember that whole, is it matter? Is it energy? Is it a particle? Is it a wave? The matter's acting like a wave. Okay, and they've proven that. Yuck. All right, so I'm just gonna give you just a little taste so you understand, because I know some of you are gonna be taking calculus and such eventually. Some of you might be doing it right now, but you know, hopefully from 7th or 8th grade math, the formula for a straight line, y equals mx plus b, right? You can describe a line on a 2-dimensional quadrant. Some of you are doing things with parabolas, okay? And you know that you can change numbers and signs and change the direction that the parabola opens up or opens down, left, right, whatever. And that's has to do with x squared. So there's a way to describe a curved flat line. Okay. And some of you might eventually know that there's a way to calculate 3-dimensional shapes, okay, like this ellipsoid. So even though you can't do the math right now, I sure as heck can't do the math, never have been able to, for something like that. Somebody can, all right? It's been figured out. And so these shapes can be described with formulas, okay? All right, end of that story. Here's my silliness for the day. Each sublevel letter actually has an official name, okay? Officially, S is for sharp, P is for principal, D is for diffuse, and F is for fundamental. I don't know why, it doesn't matter, okay? I think this works a lot better, okay? S is for spherical, because that's the shape. P is for peanut. You guys have seen peanuts in the shell before, right? They kind of look like a dumbbell, that dumbbell shape. So I go with spherical, peanut, the D orbitals, 4 daisy petal sets, and a donut. You saw that donut in the middle. Okay. And then the 7 F orbitals, I was calling them freaky flowers, whatever. They're just too much, too much. Okay. So one other thing. So again, spherical, peanut, daisy and the donuts, freaky flower. That works for me, right? I like alliteration anyway, so that works. It sticks in my head. I kind of have a visual of those wackadoodle shapes. All right. So one thing to keep in mind is that not every energy level has all the shapes, has all the sublevels. I'll show you that in a second. But every single energy level has an S orbital. So there's something called the 1s, then there's the 2s, 3s, 4s, 5s, 6s, 7s. Okay, and they're kind of like hollow. You can imagine them as like a hollow ping pong ball, hollow tennis ball on top of the ping pong ball. Softballs aren't hollow, but imagine that the other 2 were inside of that. Volleyball and a basketball. Sorry if I left out your favorite kind of sporting equipment, but the idea is that each of those S orbitals tucks inside the other, kind of like these nesting Russian dolls toys. Okay, so each of them, and there just happens to be 7 too. How convenient, right? So this would be the 1s, I'd be the tiny doll. The 2s would be a bigger sphere, which would be encompassed by the 3s, and the 4s, and the 5s, and the 6s, and the 7s. All right, let's see, watch these real quick, and hopefully some of their shapes will help you understand. There we go. Which one's which? I don't remember. Okay, here we go. So some creative people made these. These are just SMPs. And maybe there it goes. Here's the 1s orbital. Remember, at the intersection of all the axes would be the nucleus. Here comes a 2s orbital. Bloop. Here's the px, peanut, dumbbell, py. I don't know why they put the y's horizontally. This really bothers me. And then pz. Our book does it too, so I guess that must be a thing. And voila, atomic orbitals. And then the 3s would come in around all of that. And then the 3px, 3py, 3pz. Okay? Nutsy butsy stuff. Crazy, crazy stuff. And then this one is even crazier because of the music. Orbitals. Those daisy petals. So 4 daisy petals So now you've got a nice little earworm for the day, orbitals. But I think that, for me anyway, it helps me to see things in 3D. I don't visualize in my head very well in 3D, so I'm glad we have computer graphics so you can see that. So again, they all overlap on top of each other, and the basic shape of the atom with all those clouds kind of look like a balloon creation, right? It's basically spherical, okay? And again, it's 90% probability you'll find the electrons in those regions with a certain energy level, but it could be outside of it. All right, let's go back to the periodic table real quick. Here's the coolest thing. Again, this is period 1, period 2, period 3, 4, 5, 6, 7, and remember the bottom 2 are period 6 and 7, but there's something going on here. So the first 2 columns are what we call the S block, and elements in these 2 columns have 2 valence electrons. They only have their last outermost electrons are in an s orbital far from the nucleus. We'll talk about the importance of that soon. Okay, so again, 1, 2, 2 electrons. This one has 1 valence electron, this one has 2. We jump the gap. 1, 2, 3, 4, 5, 6. Px, Py, Pz. Px has 2, Py has 2, Pz has 2, 6. So these elements are what we call the P block, these 6 columns, except for helium. We'll talk more about that too next week. And their last electron goes in a P-shaped, peanut-shaped dumbbell orbital. Okay, remember counting these? We had 10, 5, the daisies with the donut, right? 5 times 2 is 10. Transition metals in the center portion of the periodic table are their last electron goes into a d orbital. Okay. There's a little weird glitch here where it goes from 4 to 3. I'll talk more about that on Monday. Okay, and then these last 2 down here, remember we counted 14. There's 7 f orbital shapes. 7 times 2 is 14. These lanthanides and actinides, their last electron goes in an f orbital. Again, the numbering gets off from the period number. The most important things that you have to really focus on are the s and p orbitals. 2 and 6 makes 8. That's an octet. Those are the valence electrons for the elements. And that is a super important thing for predicting what chemicals will form in chemical reactions, how those elements will react, how they'll behave in solution, all sorts of things, okay? But yeah, we'll come back to that a lot. Okay, so last little bit before we talk about the lab. Principal energy level or principal quantum number of 1, it has 1 sublevel, has 1 shape. That's the s orbital. End of story. Okay. Hydrogen and helium on the first line. Hydrogen has 1 electron because it has 1 proton. Helium has 2 electrons, 2 protons, right? That s shell, that 1s is full. So we have to go to another layer on our atom onion. Okay. Second energy level is that next layer. At the second energy level, there's 2 sublevels, 2 shapes, s's and p's. The s orbital can only hold 2 electrons. P's, all 3 of them hold 2, so that's 6, 2, and 6 makes 8. Okay. The third energy level, there's 3 different shapes possible, S, P, and D. That gets you to 18. The fourth energy level, there's 4 possible shapes, S, P, D, and F. Okay, and that adds up to 36. And it turns out that the sublevel squared, or n squared, gives you how many orbitals total. So let's go back to this. 1 squared is 1. Okay, 1 orbital. 2 squared is 4. There's 1 s and 3 p's. 3 squared is 9. Third energy level, you have an s, 3 p's, and 5 d's. Makes 9. Fourth energy level is 16. And that principal quantum number squared tells you how many total orbitals you have, and each orbital can hold 2 electrons. Okay, so at the first energy level, there's only an s, so there's only 2 electrons. At the second energy level, there's s's and p's, so there'd be 8. The third energy level, there's s's, p's, and d's, so that gives you 18. Fourth energy level, s's, p's, d's, and f's, 32. Okay. So I know this is crazy stuff, and hopefully, like I said, as we go through this more Monday and Tuesday, it will make a little bit more sense. And if you don't get it right away, it's okay too. Does anybody have questions right now? If you think of something, chime in. I want you to go to the material that popped in yesterday. This is the slide deck for the virtual lab. We are not completing it today. It is not to do today. It's not due Monday. It's not due Tuesday. It's due next Wednesday. So, but please don't rush through it. So this is what you're going to be typing on. And at the top is, you can click on that to get to the website, but I think I also posted it in the classwork for you. So either way, you can, I don't know how you're going to do it, but you can figure it out. So, oh, I just realized something. I think I did mine backwards on my answer key. This is the website. So there's a home page, and then this is just a copy of the slide deck. This is tells you that the different colors of light have different energies. We've been talking about that. We know how to calculate those, right? And that energy the light has to do with the moving of electrons. If they get excited, they absorb energy, they give it back off when they fall back to ground state. Every element has its own unique fingerprint or spectral lines, and the spectroscope is the instrument we use to look at the bright line spectra in the laboratory. Okay. Up at the top here, there's a tab for continuous spectrum, emission spectrum, identifying elements, and then the last tab is identifying the unknown. So when you look at the slide deck, this first one is just kind of testing your prior knowledge. Shortest wavelength of visible light in a continuous spectrum. If you don't remember what that is, you should go back and look at our notes from earlier in the week. Longest wavelength of visible spectrum light. Okay. What's the difference between a continuous spectrum and a bright line spectrum? We went over that also on Monday. I think we did that on Monday. And how are they the same? How can you use a bright line spectrum? How can a scientist use them? This one, you're going to go and click on the tab that says identifying elements. You can choose any of the four. There's more than 4 elements. You can choose any 4 elements you want, except for hydrogen because it's already done for you. So these little rings are movable, and you would put them on the V-E-E-Y-O-R. Violet is V, B is blue, green, yellow, orange, red. Usually we say it Roy G. Biv, but we've taken out indigo because it's really close to purple. It's hard to distinguish it from violet. So you're going to look at here's an explanation about continuous spectrum. Here's an explanation about emission spectrum. And then here's the elements. So these are sample spectral lines. Again, we would see these with our diffraction gratings in the classic code. So violet, blue, kind of in between, and red. Let's see what they picked. Oops. And violet, blue, and red. So there's actually more than one blue line or bluish line. I see one kind of in this region, but that would be hard probably to mark since there's not a letter for it, so I'm not going to worry about that. Probably don't want to do argon. Sodium might be a good one. Copper's okay. Gold is kind of complicated. Definitely don't want to do vanadium. Maybe potassium, nitrogen, helium. I'll let you decide. So these are the actual colors of lines, spectral lines that correspond to electrons going up and down the stairs in the orbitals. So pretty much done for today. I don't need you to do anything on this. If you wanted to do something right now, maybe do this part from your prior knowledge, or go back to here and look at the spectrum and see what it says there. I am not going to ask you to turn any